Today I'd like to talk about this 8031, 8051 microcontroller system that I built with respect to using the SDCC compiler. So there's a C compiler out there that I could actually run and generate an Intel hex file that I could download into the system. So today we're going to talk about that. So today we're going to talk about the SDCC small device C compiler that is in a public domain, and it has the Intel MCS 51 and I have the 8031, so this would be a good compiler that I could use. I could put on my system to run. I currently had been programming in assembly and wanted to take a look at this compiler that's in the public domain. It seems it's pretty readily available, so wanted to download that and give that a shot and see if I could get that to run on the system that I built. So to download it, I went to the SDCC home download page, and then there's a SourceForge download page that has a link to. So I clicked on that and I went to the SDCC Win64 directory, and I loaded the version 4.2.0. So I went in here and loaded this. So I downloaded this and I loaded it in my machine. It's not very big. It loaded quite fast, and in my Windows 10 64-bit machine. Of course, there's a lot of other versions for Linux and the Mac that you could also choose. So it seems like there's a lot of systems you could put this on to experiment with. So the other thing that I found in this project that was that was interesting, that I needed another tool that was useful, was this D52 Disassembler. So I downloaded that. You could download it from this bipom.com, and so I downloaded that, and by just clicking on that, another small file, and so I made a directory for it and unzipped it, and placed it over here. And this is a disassembler that comes in handy. So what it is, when you compile, it doesn't give you all the information. Like when it makes an Intel hex file, it makes an Intel hex file, but it doesn't give you all the information. So by using the disassembler, I could see exactly what's going into my processor, which I found very helpful. So I put my the projects I'm going to work on today in a subdirectory, and I have to use the command prompt in Windows. So I found it useful to make a shortcut of the command prompt and put that into your projects directory, and then copy where you're starting at, and go in here and click on properties, and you want to change your start, and it just makes it easier to get to the point where you're running from, and hit OK. So we're going to take a look at the first very simple program that we're going to compile and put inside our 8031 system. So it's called add8bo2. So it's a simple C program. I'm going to open it up with Notepad here. So we'll edit with Notepad, and we'll make this the only file we want to see. So it's a very simple little program, and you have to include 8051, and then so these are character parameters. So I set var1 to 5, var2 to 6, var3 to 7. This is the initialization part, and in my main I'm going to put an endless while loop. And I have to do this because if I just put the code in, when I end it, if I put it in without this, it'll run one time, and then when I end it, it's going to initialize all the memory, so I won't be able to see the results of this add. So if I put a while loop in there and then I just interrupt it by hitting a reset, I could see the results of var3. So what it's going to do, it's going to var1 set to 5 and var2 set to 6. So var3 is going to be equal to 11, so because 5 and 6 is 11. Initially I did initialize it to 7, but I wanted to change it to 11. So anyway, this is a little simple C program that I'm going to compile and I'm going to show you how to compile that real shortly. So to compile it, I'm going to go to that command prompt I just put together, so in my projects folder. So I hit the command prompt, and I want to get to the directory where this is in. So the directory, I'm going to go to capitals and hit add 8-bit 02. So that'll get me to the directory that I want to get to, and you could see the C file in there. So what I want to do is run SDCC. So, but I want to do a couple of things here. So one thing I'm going to do is start the location where I want to put the program, because my memory, where my user memory is, it's at 800 hexadecimal. So that's why I put this command in, and then I want to put where the stack is for the data memory, because the compiler uses a stack to store variables. So I want to start at 30 because I have the registers are in location 0, and there's other things that I didn't want to disrupt. So now I want to type add 8B02 for 8bit02.c. So this should compile it. So I hit that, and it's compiling with no errors. So if I look into that directory now, I now have a whole bunch of other files. So this did make an Intel hex file for me. So one of the first things I want to do is I have to put this in a little bit different form to be able to load it into my device. So I want to make a copy of it. So I hit Control C, then Control V, and I want to change it to a .txt file. So I go back here and I put .txt. I like to make it capital TXT. So I change, it's just a copy of the Intel hex file. So I'm going to open that with Notepad, and you can see it in there now. And I'm going to select everything, and then I'm going to go here, and I have to do some things. It's called blank operation. So remove unnecessary blank and ELL. So then I'm going to select it again, and then I'm going to do a replace. So I'm going to put find what. It's just a space, and I'm replacing it with nothing. So I need to get it in this pure ASCII format without any line feeds or carriage returns that Notepad kind of sneaks in there. So I want to save that. So I had to go do this little edit to get that in the right form. So now I have Terraterm running where I can communicate to the microcontroller, and I want to load this file now. So the way I do that is I have to use this E command. So I type E to load the hex file. So I hit E, and then I'm going to hit the write enable, turn the write enable on. And so I'm going to hit send file, and now I have to go find that file now to load, and that's always an issue. But I think I have a link here on my desktop. If I can find it. Oh, there it is, 8031. So I go to it's projects video, and it's in here. There's the TXT file. So I hit open. So now it's loading into my microcontroller, and so the load is done. So now I want to do a check. So I hit K, and I do send file to verify that it got loaded. So I hit open on that. So when it's compiled, a compiled version is always much greater. Assembler version of this would only be a few instructions, but you can see what the compiler does. It's many instructions. So that all loaded good. So what I'm going to do now is look at the data memory. So I type D, and I know in this area in 30, there's a lot of garbage in there right now. Just various numbers, but it's going to put the first variable into 30 and the second into 31, and the result is going to be in 32. So this is going to be a 5, this is going to be a 6, and this is going to be 11 when I run the program. So I'm going to run the program now by typing the J command. So I do that. So now I'm going to interrupt it by hitting a reset. So I hit the reset, and now I'm going to type D again. So when I look in here, yeah, under 30 now, I do see the 5 for variable 1 and the 6 for variable 2, and B is 11. So it did the 8-bit add. So that was a successful program. So the compiler does give you this file called the RST file. So let's take a look at that. And I believe that's like kind of the final results of it's an assembly listing, and it's the final results. So you could see where everything starts at 80. So you could see here it is moving 5 into variable 1, 6 into variable 2, and a 7 into variable 3. So that's the initialization part. So in the run part, this is actually the little run part here. It moves, it starts by moving variable 2 into A, then it adds variable 1, and then it moves A to variable 3. So it's using kind of a stack. It's using this data memory stack. Then it just jumps around in a loop. So it goes from here to there in an endless loop. So when I hit the interrupt, when I hit the reset, it finally loads that 11 into 32. Now the RST file doesn't quite show all the instructions involved, as there's libraries that are kind of hidden in the compiler. So a good thing to have is a disassembler. So I'm going to show you the disassembler here, and I made what I do is this disassembler could read the hex file and then give you a listing from the hex file, assembly listing from it. So what I'm going to do is I'm going to copy this hex file here, and I'm going to go to a directory I had stored away and paste the hex file into it. So to run the disassembler, I did a similar thing. I made a command prompt that'll take me into this directory where the disassembler is. So we're going to make an assembly listing from that. So I'm going to run that. So the command I want to type is D52 and -D, and then I type the name of the file. It was called okay, the one other thing I want to do here is also change this to hex. I think by default it reads a hex file, so I'm going to change this to hex. And so I'm going to put the name of that file in there. It was called addb802.hex. So I'm going to run that, and it went through the disassembly process. And if I look here, I made a new file called D52. So I'm going to go back and take these two files and put them back in the project directory. I made a directory in there called disasm. So right now there's nothing in there, but I'm going to paste those two files into it. And so we're going to take a look at the hex file. Show you what that looked like first. It's just the standard Intel hex file. So now this disassembly file, we're going to take a look at that, and we'll go into this a little bit more. Disassembly file has all the instructions involved, and where the RST file might not have every instruction in it because there's kind of hidden libraries in the compiler. But you can see this pattern in here where it does move variable 2 into A. 31 is variable 2, so we can line that up with the RST file. That's the same as this line at 86B, 86 Baker. So we'll look at that, and you can see this 86 Baker over here. So this is the disassembler. So these instructions are the same, and it loops around just like it did in the RST file. So it's the same instructions, but what you can see that you can't see completely in this RST file is there's a lot of things, a lot of overhead in the compiler. So there's a lot of jump arounds, like it jumps in at the origin and it makes space for interrupts and stacks and things. It makes a lot of space for things that this program doesn't even use. There's a lot of things where it initializes the stacks, initializes memory. There's a lot of jump arounds, but eventually it does get to the same code that was in the RST file, but there's a lot of other stuff. So you could go through that at your leisure and analyze that on your own, exactly what the program is doing. The compiler has a lot of artifacts. Now if you wrote this for yourself in assembly, it would be a much shorter program. So I'm just showing you maybe the insight into a compiler and how it works. So that's it's an interesting thing. So if we go back and look here for a simple 8-bit number, yeah, it just does the add right here. We're adding var1 and var2, and this is an 8-bit computer. So and then it moves it into var3. So it's a very simple program here. So the second program we have is still a simple program. It's called add16b01c, and we're going to open that and take a look at that. So it's similar to the previous program, except instead of a character, an 8-bit character, we're going to use a 16-bit integer. So we're going to add two 16-bit integers in an endless loop, and we could take a look and see how that works. So it's a similar process again. We're going to compile it. So to compile it, we'll go into the project. Let's see. So to compile it, we're going to go and let's see. Okay, so we have our command prompt here. So we're going to run this, and that'll take us to the directory. So we want to go cd. It's called ADD 16b01. 16b01. So we're in that directory now. So we're going to run the compiler again in a similar way as we did before, SDCC, and we want to get the code location at 800 and the data location at 30. So this is called ADD 16b01.c. So we're going to run that, and hopefully we'll have no errors. So we ran that. So if we look back in the directory, it made a lot of more files now. So we need to make our hex file that we can load. So we're going to copy and paste that, and that's going to be now called, we're going to call it .txt, and we call it that because Notepad kind of adds line feeds at the end. Some of the editors, they add things that you don't really want to add. So we're going to go and go through this process now. It's called blank operations and remove ends of lines. And we're going to go and do a replace the space with nothing. So we hit replace all. So that's all ready now to be loaded. So we're going to load this now. So we go back to our processor, and we're going to give it the E command, and we're going to upload this. I got to hit the right enable and go and hit send file. So we have to find that file again, and it's in this directory. So it's this txt. So that's loading the program. So just add two 16-bit numbers. It goes through an awful lot. It'd be much easier to do in assembly, but there's a lot of overhead with when you use a compiler. So now we're going to do our little check here to verify that the program was loaded. And so we kind of repeat that, and we were looking for these good checksums. Okay, so now we're going to look at our internal memory around 30. So around 30 we have a bunch of garbage in there. So we press J to run the program, and that runs the program. Then we're going to interrupt it by hitting a reset. Now we're going to push D again. So now we could see at 30, we could see the results here. So this is our variable 1, which was 5, our variable 2, which is 6, and this is the result, which is 11. So it actually, now these are 16-bit numbers, so it takes two 8-bit numbers and puts them together. So you can see here that they're actually read, this would be like the most significant byte, and this would be the least significant byte. So it did, it ran successfully, and we'll take a look at that program a little bit. So if we look at this RST file now, we could see what the program did, and there's a lot of overhead with the compiler, but we're just going to go to the main part of it where it adds the two variables. This is where it initializes the variable, so now it's putting the 5 into area 30 and 31 in RAM area 30, 31, and variable 2 goes 32 and 33, and variable 3 is reserved for 34 and 35. Now there's things with compilers like destructors at the end where it clears out this memory, so that's why we interrupt it. So we were able to look at the memory without clearing it out. So it's interesting how it loads the variable. It does a move, and it does it does the move. So it seems to add 1 to it. Maybe there's a carry bit that it's looking for. I'm not too sure. We'll have to look at and investigate that a little bit. But this is the area where it did the final the add. So it moves variable 2 into A, and then it adds so variable 2 is 8-bit, and then it does an add, and then see it's moving. It's like adding 8 bits at a time, but it also does an add with a carry. So this is the order. This is how you do a 16-bit add. So that's pretty interesting there. And so we'll take a look at the disassembler next to see if it comes up with the same code or not. So to get the disassembler working, we'll go back to our main directory, and we want to get our Intel hex file and copy that. And we're going to move it to our disassembler area over here, and so we're going to paste it in here, and we're going to change this to a hex file. So now we're going to run our command again. So we run d52-d, and it's called add 16b01 16b01.c. So we run that, and couldn't find it. Oops, I made an error. It's not C, it's hex. So hex. So now it ran. So I'll grab these two files again and move them to where the project is here in the disassembly area. So now we'll open up this file here. So now you can see the disassembled version, and you can see over here the similar instructions again where it does the add carry. So this is interesting, yeah, the way it loads it into 2 bytes to make a 16-bit word, and the ordering that it does is interesting. You could go through that at your leisure, but it's interesting to see how a compiler works. Now we're going to take a look at our next program, and this program it actually does a subtraction. So now this third program we're looking at, it takes 5 minus 6, which is equal to minus 1. So this is kind of like a signed manipulation here. So so we're doing a subtraction here. So we're going to run this program. We got to compile it first. So we go take a look at our directory there. It's nothing in there right now. So to compile it, we have to, maybe if we go back to one of these places here, I'm going to go back up one directory, and now we're going to go to change the directory, add 16-bit 02. So that's our subtraction. So now it's a similar command, SDCC dash code loc o x 0800 and data location o x 30. So now it's ADD 16B02.C. So we compiled it now, and you see it generated all these files. So the first thing we need to do to run our program is convert this Intel hex file to a text file. So type .txt. Want to get that in capitals, and we'll open Notepad. So edit with Notepad, and we want to do this blank operations. Remove unnecessary blank and EOL, and then we're going to do a replace. Replace is Control H. So we hit replace all to take away all the blanks. So in 12 areas, the blanks were turned into nothing. And we'll save that. So now we're going to go to our Terra term, and we're going to load this file. So we're going to hit our E command and hit our write enable and send the file. So we're going to hit send file. And we'll go back to the directory of interest. And okay, so the file is downloading. So now it's going to subtract. It's going to do 5 minus 6. So we're just showing you how a computer does 5 minus 6, a very simple instruction. So I'm going to turn the write enable off, and I'm going to do a check now to verify that the program was loaded properly. Otherwise, I'll go crazy trying to debug this if it didn't load properly. So it loaded, and I'm getting good checksums. So I'm going to hit the D command, so you can see what was in there from before. It was 11, 5 and 6 is 11, but now I'm going to run the program. So I hit J to run the program. Then I interrupt it by hitting a reset. Now I'm going to hit D again. So if I look at 30, I have the 5 and the 6. But so this is 30, this is 32, and at 34 I get FFFF, which is -1 in signed math. So what I want to do now is look at that RST file to see how it does do a subtraction for two 16-bit numbers. So you could see it in here. The sequence of operations, and it's somewhat different when you do a subtraction. You have to clear, I believe you have to clear the carry flag first. So you could go through this at your leisure and try to figure out how this thing worked. With these instructions, how does it come up with FF? So we'll also do the disassembler just to show you that it can also disassemble that. For this case. So what we have to do now is let's see, we have to get that file, the hex file. So here it is over here. So we're going to copy that, and we're going to go to our disassembler directory, which is up here, and we're going to paste that in, and we're going to change this to hex, H-E-X. Okay, so now we're going to run our command prompt for the disassembler. So we're going to type D52-D, and it's called add 16B02.hex. So now it made our D52 file. So we're going to take these two and cut them and get back to our project directory over here. We made a disassembly area which has nothing in it, but we'll paste that in there, and we're going to open up Notepad So we want to see these instructions again down here. These are the instructions in this area. So it wastes an awful lot of memory, the compiler. So I mean, I could do this in maybe this many instructions, maybe 10 instructions, but it's only up to 874, so it's using like a kilobyte of instruction memory to do something that simple. So I guess on bigger programs where things get more complicated, yeah, the compilers get more effective. But for simple programs, assembly is best. So if we look back here, it's the same type of instructions again. It starts at 874. This move A. So if you look, it's 874. These are the machine code instructions for that. So now we're going to show you the last program here for today. And we're going to edit that with Notepad. So this is the C program. So what we're going to do now is add two floating point numbers. So these are 32-bit IEEE floating bit numbers. So one's 5 and one's 6. And it's a similar thing to before, except instead of fixed point, we're going to do floating point. So it's going to be var3 equals var1 plus var2. So we have to go compile that. Right now we don't have anything besides the C file in this directory. So to go compile it, we have to find the right directory here. So we're going to go back up one directory, and we're going to go to our directory where we're going to compile this. So it was add FLT01. So we're in that directory. So we're going to run our SDCC compiler. So it's code location OX0800. It just happens in this processor, the user memory, that's where it starts at. And data loc OX30. So we want to do addflt.c. Oops, got to get the 01 in there. .c. So we'll let that run. So now if we look in here, yeah, it generated all this other stuff here. So the one thing we want to do is make a text file from our Intel hex file. So we're going to put that over here and rename that txt, and then we're going to use Notepad to edit that. So now it's a huge program just to add these two floating point numbers. See, there's libraries in the compiler that don't show up on the RST file. So the only way you can get it is by looking at the Intel hex file and disassembling it. So anyway, we're going to get this in the right format that I need to be able to load it. So we're going to do these blank operations, and then we're going to replace all the blanks with nothing. So there's 28 replaces there. So we'll save that. So now we're going to load this program. Okay, so just make sure my communications is there. So to load it, I hit the right enable on the card, and then I'm going to send the file. So I have to go up directory to the txt file. So the program's loading now. It's a much bigger program now to load, just to add these two 32-bit floating point numbers. So, but anyway, it's loading from the compiler there, and should be done soon. And it's done. So now we're going to go check it. So we hit our K command, and I'm probably almost out of memory to be able to do such big programs. But anyway, we're checking that, make sure we have all good checksums. And so it's going through that process right now. Should be done very shortly. So it's in there and running. So there it goes. So now we're going to look at our memory here, And we have the results from the last run in here. This is still FF. But we'll go do, we'll run the program. We'll hit the J command. That'll jump to the program. So the program's running now. So I'm going to interrupt it and press D again. So let's see what we have here now. So we have, so this is our first 32-bit number. And I believe you have to look at it like this is the first, second, third, and fourth nibbles. So it's going to be 40 A0. So let's see, that should be 5. So we have a little program here we can use, this IEEE floating point calculator. So if we put, we'll put the number 5 in here on floating point and hit show. So you can see how it's 40 A0, 40 A000. So the next number was 6. So we'll put that in. So you can see that number over here in the memory. So the answer should be 11. So that's 40. Well, 6 is 40 C000, C40 C000. So the answer was 11. So we'll show that. So that's 4130 0000. So you can see here is our 4130 0000. So the program was successful and computed the right value for that. So we'll take a look at that RST file that it made to see how it adds the two floating point numbers. So yeah, you could see in here where it's doing that immediate setting of those parameters 5 and 6 and 7. But when we look at when we look at the add, it does a call. So it's doing a library call, and this library, it's located at location 08AA, which on this listing, it doesn't have it because it's in a library. So a lot of compilers have libraries that are kind of hidden. So what we have to do to figure out to reverse engineer this is the reverse engineering process of a computer. In order to do that, we have to use our disassembler. So we'll go yeah, we'll get through that. So we're going to take our Intel listing here and copy that, and then we're going to go into our disassembler area and paste that, and we're going to rename that hex, HEX. So we're going to run the disassembler now. So it was D52-D, and it was add FLT01.hex. So it ran through that. So now we want to move these to our working directory. So there's some directory gymnastics there in getting around, and we'll paste that in. So now we'll open up our disassembler, and so we could look in here and maybe find the area with the RST. It was it was 894. We should see this call at 894. So we'll go try to find 894. Just to make sure it matches up. So yeah, you could see this call here. So the call is at 8AA. Okay, now the RST file won't show you what is an 8AA, but this disassembler will. So if we look for 08AA, we go find 08AA, which is right here. It starts. It's a pretty big routine here. It first goes to 96. It has like stacks and all kinds of things, all kinds of manipulations. It's a pretty big program, and it would take me quite some time to go through this. You just have to accept that it's good. If you wanted to go in and reverse engineer it to figure out what it did, this is how you would do it. You have to do like kind of a hand assembly. So the disassembler really helps you. So anyway, this is very interesting if you have to reverse engineer compilers or understand how the compiler works. Sometimes we have safety critical software and they don't trust the compilers, so you have to actually go into machine language and assembly or disassemble it to prove the compiler is doing the correct thing. So this is the process you need to go to when it becomes like safety critical. There's standards that you have to follow to verify that the compiler is actually doing the right thing. So anyway, I hope you like to see how this SDCC compiler worked. I was able to find it and load it into like a processor that I built myself. So it was very interesting. I hope you enjoyed this. I know it's kind of boring and very tedious and mind-boggling, but this is what you have to go through to be a good software engineer.